Okay, everybody, what I want to do is finish up periodic table here, but just a quick note on page 12, which is a little bit more about ionization energy. And I just wanted to show you this and do it maybe together here as far as this works with IE. And again, if you look at page 12, you're going to see a table here. And across the top is a period 3 element. So you have period 3 here going across this direction. So you're going left to right. All right, and you'll see these I1 versus I2 versus I3 versus I4 kind of thing. And these are ionization energies. First ionization energy, second ionization energy, third, and so on. And basically what the first ionization energy is the energy needed to pull off the first electron. All right, if you want to pull off a second electron, then you would call that the second ionization energy and so on. All right, so what we see here is we see an interesting pattern as we go down. In gray here, this grayish box here is the first ionization energy. And what we see is an interesting pattern as we begin to fill these off, okay? And let's just say, so sodium, if you pull off the first electron, that would end up giving you, for sodium, that would give you an Na+1, okay? And what we find is that after that first electron, there's a huge jump, okay? And we do know that for sodium, you have a 1s2, a 2s2, a 2p6, and a 3s1. And what we notice is that once you pull off that outer shell electron and you reach a noble gas core, we hit some stable configuration. We know that already. Now, we know that basically by looking at the electron configuration, but that's not proof. What we do is we get that from the ionization energies by looking at that data. And we see there's a monster-sized jump when we try to pull off something from the 2p6 where we know that electrons are all paired up. So what scientists do is they confirm this. They know they get the correct ion. They know an element is stable after they see that first big jump in ionization energy. So this is group 1, group 2, group 13, 14, 15, 16, 17, and 18. So you can see, really, when you get past this line, the line's going to show, okay, a large jump in IE, okay, which is what you see. So you can see that magnesium, you lose the first electron, it's going to be 737. It roughly doubles for the second, and then you get this really large jump. And that's telling you that you're stable at magnesium +2. That sodium is stable at sodium +1. Okay, even aluminum, 577, 817, 2745, and then jumps up to 11,000. So that's going to tell you that aluminum is stable. So you're looking for that first big jump in ionization energy. That's really what this really looks like. So I just wanted to just kind of show you this a little bit, and this way everybody gets an idea of what it really means. So your trends across the period is we know that IE increases across period. Okay. Another thing you may want to get out of this is that the ionization energy increases as more electrons are removed. You may want to make a note of that too. Okay. We can say that also. We could say explain why the radius is indirectly related. Okay, increased nuclear charge. Okay, pulls electrons in closer. Okay, increase attraction. Okay, your lowest radius, important to know. Okay, and increased energy is needed to remove additional electrons. Okay, so if you want to keep removing them, again the nucleus is still the same size, so it's pulling harder on less electrons. Okay, and then how does the data help us? Okay, large jumps in IE indicates an element has reached the noble gas core. Okay, and that associates with your S2, right? And your P6, 1, 2, 3, 4, 5, and 6. All right, so that is the S2 filled shell. So that tells us. All right, so just an interesting way the data kind of fits our idea. And I just wanted to show you